The intermediate value theorem is a result that's a bit more abstract than a lot of what we see in this class. It's a bit more advanced, in my opinion, than what we see in this class because it doesn't quite have that nice find a value feel to it, and it also has a sort of looseness in terms of how it works that makes it hard for some people to grasp. Where very roughly what the intermediate value theorem says is continuous functions don't, or for that matter, can't jump. A little bit less roughly, if you have something that is continuous, if you have a function that's supposed to go nice and smooth from one place to another, then it can't avoid points along the way. To be perfectly exacting, the statement of the intermediate value theorem can be written as something to the effect of: if f of x is continuous on the closed interval from a to b, and value s is such that f of a is less than s is less than f of b, then there exists some value, maybe more than one, c, in the open interval from a to b, such that f of c is equal to s. Again, that's a very exacting definition. Really, the best way to understand what the intermediate value theorem says is to look at a picture that will give a bit more of a clearer indication that if I have something like a function f that's nice and continuous from a to b, it has to get through all of the things between a and b. And it might do that more than once, it might only do it once, but it definitely has to do it somewhere. And you can do this for any type of value, but the one that's the most useful, the one that we like the most here, is that you can use the intermediate value theorem to say that if a function that is continuous goes from negative to positive, that means it must have hit 0 at least one time on the way there. And that's what we'll get a quick example of here, just to see how that works. So for this, we want to show that the polynomial g of x equals x cubed minus 3x minus 1 has a real 0 between x equals 1 and x equals 2. So to do this, we're going to take g of 1 and g of 2 and evaluate each. Where at 1, we'd have 1 cubed minus, sit with me, 3's and 2's, 3 times 1 minus 1, and this would give us a value of negative 3. Meanwhile, at 2, we'd have 2 cubed minus 3 times 2, which that was a real nightmare if I wasn't careful, minus 1. Pull all that together, and you get a value there of 1. Where, because this goes from negative to positive, and it is a cubic function, it's going to be nice and continuous, so it had to have crossed 0 somewhere in the middle. That is, because it went from positive to negative, negative to positive, although the other direction works for the same reason, it must cross the axis. Can't go from being negative to positive without crossing the axis. For a picture, it looks something like this in that way, where the intermediate value theorem doesn't tell us anything in particular about what that 0 is, or even if there's only 1, it could cross a whole bunch of times in there, but here we only get the 1. And in this case, there isn't a nice way to be able to get what that value is. It ends up being about 1.88. The nature of these roots is that they sometimes can be a little bit unpredictable, and we're very rarely going to get nice values from them if we have to call upon the intermediate value theorem. So it does take a little bit of inspiration to think to use it, and to think to use certain values in there with it. But it's worth mentioning, and I like it because it is one of those kind of cool tricks that most people wouldn't think of when they're looking at this kind of thing mathematically. It's got a subtlety to it. It's got a sort of artfulness to it that a lot of formula manipulation, sometimes it can lack. Anyway, that's the last thing I'm going to put in here. Technically, there's a bit more in this section about formally graphing polynomials, but speaking of things that I think aren't very artful, I'm not a big fan of that sort of process. It can be useful, but really what I think is most important is being able to describe these general behaviors for yourself in the context of examples. That is, being able to take a graph and intuit some useful things about multiplicities of roots, or end behavior, and then do the reverse. Talk about a function and be able to say, okay, this is what it roughly should look like, rather than having a big detailed picture that only really works if you have the right setup to be able to use these tools that we have. It's all very back-ended, and to me, not incredibly interesting, just time-consuming. So I'm not going to ask you too much about it. There might be things where you'll have to throw up a multiple choice graph, but this sort of thing is more important to me. Anyway, that's what we have here for 3.1 and 3.2 for this week. Next week, we're going to continue extending this stuff off to talk about things with a bit more of a rational flavor. We're talking about tossing polynomials on top of each other and how we deal with the algebra of that instead, but that's for later. We'll get there soon enough, though.